So I can also charge an object by induction, is by inducing charge on an object. And so what I do, I get negative charge on this guy, bring it close. The electrons in the electroscope want to get away from the PVC. Why does it keep doing that? They want to get away from the PVC. Is it like building up on the glass or something? It might be the glass. I bring an object close, but not touching. So the electrons in the electroscope want to get away from the pipe, and so they go down to the leaves as far away as they can. But if I ground it and give them a path to leave, those electrons can then leave the electroscope, and when I pull the rod away, the leaves spread apart because those electrons are now not there. So if I charge it with this negatively charged rod, there's now a positive charge on the electroscope, right? Because the electrons were trying to get out. They didn't have a path until I grounded it. When I grounded it, I gave the electrons a path to leave. And then whenever I remove my finger and then remove the rod, I now have less electrons than I started with. So it's now positively charged. So when you charge something by induction, you actually get the opposite charge on it. When you charge something by conduction, you get the same charge on it. Okay. And I touch it, and it's actually working nicely now. I touch it, and the leaves immediately flow down because while I'm not a great conductor, I am a decent conductor of electricity. And so whenever I touch that, the charge flows off of me onto the electroscope to neutralize it. Or the other way around, yeah. But in this case, it would be electrons going from me onto the electroscope because, yeah. So another way of charging by induction, I get some, whatever, polystyrene, I don't know. I'm assuming that this guy's getting electrons though, because the rabbit fur likes giving them up. And because this is an insulator, it's not going to allow that charge to leak off very quickly. And then I take this guy, it's a metal plate with a plastic handle, so an insulating handle, and I just go like this, and you might be able to hear it. Maybe not. Let me try that again. Usually you can hear it. You get a little tiny zap. Did you hear it? There you go. So what happened there is that I have a negatively charged plate. I put this conducting plate on top of it. The negatively charged plate forces the electrons up to the top of the metal plate, and they're as far away as they can get. But then I touch the metal plate and give those electrons a path to leave. Now that those electrons have left, this is now positively charged. And now, if I bring it close, you can see that the leaves spread apart, right? And since this guy was positively charged, this guy is now negatively charged. And this guy is now positively charged because I've charged by conduction, right? Positive. And then if I touch it, then electrons again will flow onto it, neutralizing it, and the leaves fall back down. And yes, this is a good example of science. All right. So this stuff seems pretty mundane, right? In today's world of electromagnetism, where electricity literally dominates our lives and we produce megawatts of electricity day by day and countless numbers of electric power generators across the world. But this is how it started. It started way back in the day when people, before anyone knew anything about even science, sometimes they get shocked. I don't know what that is, but sometimes we get shocked, and that's weird. And then the ancient Greeks, found a rock that attracted little metal bits sometimes. Like, oh, that's weird too. Right? That's where it started. But then what really spurred what now has become our literal, the way that we generate power, and the machines that we use that use electricity, it started with stuff like this. It started with charging electroscopes, right? And figuring out, what is charge? With positive, negative, there's two different charges. Sometimes it's repelling, sometimes it's attractive. How can we explain that stuff? Because you can't see an electron. You literally can't see an electron. It's impossible. There's no visible wavelength of light that will reflect off an electron. So you literally can't see an electron. Yet all of chemistry is based on the existence of the electron, right? And really physics, like the physics of electromagnetism, is all based on the existence of the electron. So it's all made up and fake. Yes. Yeah. Just don't tell anyone that. Right? That's what we learned in this class. We learned how to fake it and make the general public think that we know what we're doing. Right? Okay. So that's electric forces, charging objects, charging by conduction, charging by induction. Mr. Fullerton talked about this a little bit. Remember the can and how it kept the same orientation of charge, positive on this side, negative on this side, even if it was rolling. And that's because the charge can freely move through the conducting material. If this was like a plastic can, that wouldn't work. You would get it attract, but then once this side got close, it would get repelled and it would kind of rock back and forth, right? It wouldn't work like it does with the can here. So just keep that in mind.
So would the electric field on the can be like a little like butterfly?
Yeah. Yeah. Mm-hmm. No, not quite. Okay. You're thinking about magnetic fields.
Okay.
Yeah. They would just be kind of. Yeah, yeah. But it would be more like this. It would be more like. It wouldn't be like this.
Uh-huh.
It would be more like that, and then they point out here or in here,
Okay.
right? Yeah. So it's kind of like what you're thinking, but at 90 degrees to that. Okay. All right. So that's our introduction to electrostatics, which is our introduction to electromagnetism. But we really can't go much farther without talking about fields. Fields are just like vectors. They are a made-up concept. They don't actually exist, but what they represent does exist. And actually, before I even get to that.
You mean there's
It's
not
like electrons.
You mean there's not blue arrows hitting the Earth right now?
No, there's not. There's not. There is a gravitational field surrounding the Earth that we symbolize by our concept of a field, which we can draw as arrows. But yeah, there's no... When I have this rattleback and I drop it, it's not like there's an arrow that points in the direction of the gravitational field, right? So, what?
You didn't see that arrow?
No, I didn't. Am I crazy?
Are you okay?
When I start walking, does an arrow with a V on it point out of my...
It could be infinitesimally small.
Oh, it's true. It's true.
Just don't walk towards me.
So yeah, vectors aren't real either, but they represent real things, right? So fields, at least how we draw them, are not real, but they represent real things. I think the easiest, there's two types, well there's more than two types, but there's two main types of fields. There's scalar fields and vector fields. Vector fields are something that I think you end up dealing with in calculus a little bit, right? Yes, no?
I don't remember. Maybe slope fields.
Slope fields, yeah.
Oh, yeah.
Slope fields can be vector fields, yeah. So a scalar field may be a little easier to deal with. Do you guys remember, you were little, but relatively recently they discovered the Higgs boson. You guys heard about that?
I remember. I've heard that name before.
Well, the Higgs field was theorized in the 60s, and it is a quantum field. And so like the electron field, electrons are manifestations of essentially excitations in the electron field. The Higgs field, which that again was theorized in the 60s, if you produce enough energy in a small enough volume, you should actually get an excitation big enough in that field to produce a particle that will last for a very small time. And that was actually detected, the first one, using the Large Hadron Collider, about 10 years ago now. It was big news when it happened.
I remember hearing that.
Yeah.
So they created matter out of nothing?
Oh, out of energy.
Out of energy.
Yeah.
They created matter?
No.
Okay.
E equals mc squared, right? Energy and matter are kind of the same thing. So the thing is, the Higgs field is a scalar field. A scalar field is, you can think of a scalar field as just a field that exists in space that has a number attached to every point in space. The infinite number of points in space. Okay. A temperature field would be a scalar field. So if I come in the morning, and where does the heat come in? Let's say that this is where the heat comes out, and that's the only place that the heat comes out. Okay. And it's really cold, and I come in the morning, I turn on the heater, and the heat starts flowing from this point here. After a little bit of time, the whole room is the same temperature. But for a while, it's not. For a while, it's still colder in the back than it is in the front. Well, I can talk about the temperature field in this room as a collection of numbers that are associated with every point in the room. Points in the back of the room will have smaller numbers for the temperature than they will in the front. Okay. Now, if I wanted to draw that field or produce that field in a three-dimensional computer simulation, do I have a point for every single point in the field, the infinite number of points in the actual space? No. And so we have to be a little more. We have to just say, okay, well, I'm just going to put 1 point every centimeter, every cubic centimeter, right, or at the corner of every cubic centimeter, or every cubic foot, or something like that. But just understand that a field, if it exists, it will have a value at every single point in space. And you'll eventually learn mathematics that will allow you to say, okay, well, at this particular point, I can calculate the value of the field at that point. Okay. Now, a temperature field or the Higgs field, those are scalar fields. Electric fields and magnetic fields, which is what we focus on in this class, are vector fields. So not only do they have points associated with every location in a space, but they also have a vector associated with that same. So instead of just a value like a temperature value, if we're talking an electric field, it will have the electric field strength as the magnitude and the direction, right, to give it a vector, to make it a vector field. So before we get on too far, what is this? Gravitational fields, the same kind of deal, right? If you look, these arrows show the direction of the gravitational field, right, towards the center of the Earth. If we're standing on the surface of the Earth, then it's like a two-dimensional flat surface. So in our normal everyday life, the gravitational field seems to be just a bunch of parallel lines that point straight down. In totality, there's an infinite number of these arrows, all pointing towards the center of the Earth. The farther away you get, the weaker the gravitational field becomes. Okay, and so I feel like before we're a little more familiar with gravity, so it's a little easier to understand gravitational fields as opposed to electric fields. So before we get to electric fields, let me just kind of remind you of something. If we take an object, say Logan, and put him right here, and we want to know the force of gravity on Logan, it looks like the center of the Earth is maybe about here. So that's the position vector R. And let's just talk magnitudes now. The magnitude of the gravitational force. Actually, let's not talk about magnitude. Let's be more specific. The gravitational force is a vector. It is equal to, according to Newton's law of universal gravitation, negative G times M1 times M2 over R squared. But I can also say, well, it's just equal to M times G. Right? And we calculate this using Newton's law, or we can calculate that using Newton's law of universal gravitation, but we've been using this for years, since you guys were like 2-3 years old. We've been using this to calculate weight forces, right? Weight forces, as we know, are gravitational forces. This is a vector equation, so G and F must be in the same direction, right? Mr. Fullerton showed you that the definition of electric field is simply the force, the electric force, divided by the charge, right? He goes over that in the video. And I want to elaborate on that now to make sure that you understand what that means. Because if you understand what this means, everything else that follows is a lot easier to understand. If you don't, then it's a lot more difficult to understand, which is why I like going here, something that we're very familiar with. Because I can do a very similar thing here. Sorry, this is electric field direction. It turns out that G can be thought of as the acceleration due to gravity, but it can also be thought of as the strength of the gravitational field. Okay? So this can be the strength of the gravitational field, and if I make that connection, then I can divide both sides by m, and I get it's the gravitational force divided by the mass is the gravitational field strength, which matches this identically, right? Well, not identically, but we made the Newton's law of universal gravitation and Coulomb's law very similar. The only thing that's different is that instead of masses, we have charges. So this is essentially the gravitational equivalent of this, right? What this tells us is that the gravitational field strength at the point, let's say that Logan's at, will be the gravitational force on Logan divided by Logan's mass. So the units are newtons per kilogram. Right? Here, the units are newtons per coulomb. Now, when I say newtons per kilogram, what makes this very, very, and I can't emphasize enough, very useful, is that I can get rid of Logan. I can throw him into the hole in the earth, right? But that point that he was at, the gravitational field still exists there. And it still has the same strength. And I can take a different massed person, or a different massed object, this little rattleback. I take this little rattleback and put it there. And that rattleback feels a different gravitational force, but it also has a different mass. If I was to take the rattleback's force and divide it by its mass, I get the same number that I got whenever we did it with Logan. So what that means is that I've described this point in space. What is going on? The physics of this point in space. And I've done so without the need of having an object there to actually make any measurements with. Okay? Because I've divided by the mass. I divide it by the mass. I'll elaborate on this tomorrow when I have a little more time. But that's the strength of the concept of the field. Because I can describe the physics of what's going on around the Earth without having anything actually need to be there. Okay? And the same thing happens with electric fields. I divide the force on a charge by the object's charge itself, and I get the number of newtons per coulomb. And understand this, newtons per kilogram. Let's say that I have a field strength, gravitational field strength of 10 newtons per kilogram, which is about what it is at the surface of the Earth. If I have 10 kilograms, what's the gravitational field? If I have 10 kilograms, oh my gosh, what am I saying? What's the force? 100 newtons, right? Because if I multiply 10 newtons per kilogram times 10 kilograms, that tells me the force. Well, the kilograms cancel out, and I get 100 newtons, right? If it's a 2 kilogram object, well, if it's 10 newtons per kilogram, well, then I have 20 newtons of force, right? So I'm talking about at the surface of the Earth. At the surface of the Earth, how much force is on the object? You just multiply its mass times the strength of the gravitational field. Okay. Now, why is this the same as the acceleration due to gravity? And this is where I'll end it. A newton is a kilogram times meter per second squared. If I divide that by kilograms, you put that over 1, flip the guy and multiply, and what do I get?
Meters per second squared.
Meters per second squared. So if I'm talking the strength of the field, I say newtons per kilogram. If I'm talking the acceleration that I experience because of that field, it's meters per second squared, but they're equivalent units. Okay. We didn't get nearly as far as I wanted to get today, but we'll just finish it up tomorrow. And yeah, any questions, comments, concerns?
So is Q, if Q is relatively the equivalent of N, is Q the resistance to an electric?
No, the Q will be the charge itself. Yeah. We'll pick it up there tomorrow.